So we're back to our track and field example where we're looking at sprint times and jump distances, and we've got our regression. Now, how do we actually write the regression equation? And you might think that's kind of a silly question because here it is written right here for you. But make sure when you're writing the regression equation in statistics, you definitely need to make sure that you always identify your variables. And there's two ways to do this. So one way I can do it is just write the equation, but I'm going to put a hat over the y. That means predicted y. So when you see y hat, I'm just going to write up here, y hat means the predicted y value. Predicted y is equal to 414.786 minus 45.743x. Now, if I write it this way, I have to, over to the side, write out x equals sprint time. I'll put that in seconds. And y equals jump distance. And that was in inches, I believe. Okay, in inches. The other thing I could do, which is actually my preferred way because it takes less writing, or you could write it like this. Jump hat equals 414.786 minus 45.743 sprint. And you just insert the name of the variable into the equation. And this is actually what you're going to see most often in statistical applications. You're going to see it written like this. It's up to you. You can write it either way, but this one is more concise and takes less time. Yeah?
Do you have to include units?
You do not. Just there's usually someplace in the description of the problem there is enough information about the two variables that it's clear what they mean. And I didn't strictly have to include it over here, but I do have to identify what x and y is somehow, like which one's x, which one's y. Now, the second thing I want to talk about is how do we interpret, yeah, go ahead, Aubrey.
Why does the jump have a hat but not sprint?
Because the sprint is the actual sprint time, but the equation predicts a jump time.
Oh.
Okay? And the predicted jump time is whatever y value lands on this line, but the actual jump time might be different than that because not all the points are on the line. Good question. Okay, so let's interpret the slope and the y-intercept. So here's the slope, 45.743. And we know from way back in algebra that slope is change in y divided by change in x. So it is the amount of change in jump time for each unit change in sprint time. And so this is how I want you to write the interpretation of the slope. For every 1 second, and because this is our units for sprint time, for every 1 second increase in sprint time, every 1 second increase in sprint time. So we're always looking at 1 unit increase in whatever x is. And you might want to put down 1 unit and that this is our x value. So we're always going to be talking about the increase of 1 unit in x first. The linear model, and that's our regression line, the linear model predicts a 45.743 inch, because that's our y value units, decrease, because the slope's going down, in jump distance on average. Okay. So we've got this predicts and on average, saying this isn't exactly what we are going to get for our jump distances, but on average the prediction is this is what was going to happen with our jump distances. So
Why is it a decrease in jump distance if you're increasing like
Because when you increase sprint time, you're actually getting slower. Yeah, slower runners don't jump as far. Yeah. Okay, does that make sense? Okay, so that is the interpretation of the slope, and it's just a prediction because this is a linear model that helps us make some predictions about the data, but doesn't exactly tell us what will happen for any one individual person. Now, the y-intercept is what happens when x is 0. So, for a sprint time of 0 seconds, the linear model predicts a long jump of, what is it, 414.786 inches. 0.786 inches. Obviously a ridiculous interpretation. So the y-intercept only is reasonable if it's possible for x to be 0. If that is a reasonable value for x, then the y-intercept might mean something. But in most cases, the y-intercept doesn't have a reasonable meaning. So you're going to say, so in most cases, the y-intercept has no realistic meaning. Sometimes it does, sometimes it doesn't, but a lot of times it doesn't. Because clearly nobody has a sprint time of 0 seconds. Even the Flash probably takes like 0.00001 second to get there, something, you know. Like there's a little bit. I like the Flash. He's pretty cool.
I'd imagine his acceleration would be this slow if he wanted to not fall apart.
Actually, technically, would he have been like negative something?
I don't think so. I don't think he actually goes back in time. He just goes super, super fast. Okay, I'm recording this for period 5, so let's stop this and get back on track here. Okay, use the regression line to predict the long jump for a person whose sprint time is 5.78 seconds. Okay, so if you go back and look at the graph here, I have that point labeled. I know the person that had a sprint time of 5.78 seconds had a long jump of 173 inches. But what does the line predict? What does the regression line predict that their long jump would be? So that's, what are we going to do? Easy peasy, guys. Plug in 5.78 for sprint time in our equation. So we have our jump, our predicted jump is equal to 414.786 minus 45.743 times 5.78. So this is where I would appreciate, actually I've got it, you guys, I've actually got this value. That is 150.39 inches. No, that's still not regular jump. It's still predicted jump. And here's why. We know his regular jump was actually 173 inches. His predicted jump is 150. So if we go up here and put that on the graph here, this is 5.78, 150.39. The line actually predicted this person's jump to be lower than 173 based on their sprint time. So based on like the average from all of our data, I would expect someone who had the sprint time to get this long jump. So he actually did better than what we would predict. Okay, and that difference between how well he did and how well what the line predicted is called a residual. And you'll see this thing that says resid right here. Each point has a residual that is the difference between their predicted time and their actual time. And we're going to talk about that more in just a minute. And actually, we might be talking about that next. I'm not sure what comes on the next page. So let's find what happens on the next page here. That might be what's next. Almost. The next thing we're going to talk about is extrapolation. And extrapolation is just predicting outside of the interval of the values of the explanatory variable. Okay. Extrapolation is predicting outside the intervals of the value of the explanatory variable. So here is my lowest explanatory variable. So when we're talking about here, here's my lowest value for x. Here's my highest value for x. So when I'm talking about this would be the range of the interval of values for my explanatory variable. So somewhere between like 5 and 7.3. So approximately 5 to 7.3 seconds. All of my data is in between those two values. So if I use my line to predict something outside of those values, higher than about 7.3, lower than about 5, then sometimes weird things happen. So let's look at an example. If we used our regression line to predict the long jump distance for a student who runs 40 yards in 9.5 seconds, pretty slow runner. Okay, so probably me. That would be me. Yeah, no. No, I don't know. Actually, I have no idea how fast I run anymore. I don't ever run much anymore. So the jump is equal to 414.786 minus 45, and this it's written right here, which is why I can see this nicely. So 45.743 times 9.5. Well, just looking at the line, what do you think might happen? Yeah, it actually turns out to be a negative number. Turns out to be negative 19.77 inches. So this says basically if you run slowly enough, you'll jump backwards. No. Okay, so this is clearly ridiculous. This does not happen. Even the slowest, most unathletic person could manage to jump a little bit forward. You know, they're not going to jump backwards. So this is clearly ridiculous. All right. So this is what happens when we use our regression line to extrapolate or predict beyond the range of our original data. We're going to get values that just might not make sense. Such predictions are often inaccurate, and it's because of a couple reasons. One, trends might change. Or values might be unreasonable. So when we predicted our y-intercept, that was actually another example of extrapolation. That was clearly an unreasonable value, and nobody's going to be jumping that long. 414, I don't know. What is 414 inches? That's a lot of feet. I mean, maybe that's realistic for an Olympic jumper. I don't really know off the top of my head. But anyway, you're not going to run 0 seconds, though. So those values don't make sense. Okay, so I wanted to go to the next page. I have a little extrapolation humor for you. As you can see, okay, so here's the graph the person's made. Number of husbands. Yesterday, they had 0 husbands. Today, she just got married, so now she has 1 husband. So as you can see, by late next month, you'll have over 4 dozen husbands. Better get a bulk rate on wedding cake. So just a really ridiculous example of the stupidity of extrapolation at times. So, pardon me? Can you buy cake in bulk? I don't.
Even if they're in Utah.
That's pretty funny. Okay. Bulk wedding cake in Utah. Okay. So let's talk about residuals. So we had, if we go back to the person that had the long jump time of 5.78 seconds, their calculated long jump distance from the previous page was 150.39 inches. And their actual long jump distance was 173. So this is from the data And this is from the equation. So we predict with our equation, but the data actually told me how much long that person really jumped. So the residual is the difference between the actual and the predicted. So it's actual y minus predicted y. So actual y would be y, and predicted y would be the y hat. So in this case, our residual would be 173, which is the actual, minus 150.39, which gives us 22.61 inches. So you do need to put residuals, unlike correlation, have units. So the residuals will have whatever y units. So make sure you include units on your residuals. So how do we interpret a residual? Basically, we would interpret this. So I will write this down since I don't have a little line for this. So interpretation of residual. Yes, actually, the putting all the residuals together does give us a measurement of error, and actually, we will talk more about that. But good point. So the interpretation of the residual here is that the person jumped farther than predicted, right? So the student who jumped, the student with a sprint time of 5.78 seconds jumped 22.61 inches farther than predicted. The student with a sprint time of 5.78 seconds jumped 22.61 inches farther than predicted. Sometimes it's expressed this way. We could say the linear model underestimated his jump distance. By 22.61 inches. Now you don't have to say both of those things. Those are just two different ways of saying the same thing. And later on, I'm going to be having you guys look at your hand span and your number of candies you grabbed and the linear model for that, and say, well, did the model underestimate or overestimate how many candies you could actually grab with the size of your hand? Like, how much would it predict and how much did you actually grab? Okay, one more thing about okay. One thing that we have to be careful of when we're using an equation, in algebra we're used to saying, okay, if I know y, I can use my equation to find x. If I know x, I can use my equation to find y. But that is not true when we're talking about a regression equation. And so let's take a look. What I did here is I made an equation this is the equation where sprint is the explanatory variable and jump is the response variable. Then I switched them around and I made jump the explanatory variable and sprint the response variable. Now we know the correlation would be the same either way, but obviously the regression equation is different. But what happens if we gave a certain, a sprint time, or no, if I give you a certain jump distance and put that in for jump in both equations. Let's see what happens. All right, so use both equations to predict the sprint time for an individual with a long jump of 160 inches. So in this case, I would say 160 is equal to 414.786 minus 45.743 at times, and I'm just going to call this x for solving purposes, And if I subtract 414.786 from both sides,
Is that a minus x or times?
that's times. 4.786 equals negative 45.743x. So we can write that a little better. And then if I divide both sides by negative 45.743, I would get x. Okay, so in this case, what I would end up with, if I do that, as I would end up with the sprint time. So this is x. Sprint equals, I did this here, 5.57 seconds. Okay. So this, if I said using this line, that's what I would end up for sprint time. Now the second one is pretty easy because we can just substitute 160 in for the jump time. So here I would have predicted sprint time is equal to 8.257 minus 0.015 times 160, and I would end up with 5.793. They're pretty close, but not exactly the same. So why are they different? Why don't they turn out exactly the same like we would in algebra? A little mistake here on sprint time. This should be 5.857. We found a mistake. Becca Turner found a mistake. Now you are immortalized on my video. Okay, so in number one, we're using actual jump time, but the equation uses predicted jump time. Okay, so the 160, so we have y equals 160, but this is predicted jump time. This is y hat. So trying to use actual jump time to find in place in this, but this is only predicted jump time here. Number two, they're giving us actual jump time and we're trying to find to predicted sprint time. So the first one, we're using actual jump time, but the equation uses predicted, oh, sorry, not jump time. I'm saying time when I mean distance. That's what's throwing me off as I'm reading my own stuff. Actual jump distance, but the equation uses predicted distance for y. Predicted distance, y hat. So when we use an equation, we always want to use the actual value for the input to give us a predicted value for the output, but we can't go backwards with that. We can't start with an actual value and put it in where the predicted value is supposed to go and then find an actual original value. So that just doesn't work. It has to do with the actual versus predicted. Does that make sense to you guys what I'm saying? So we can't go back and forth. So you actually have to use completely different equations. If you want to use, if I wanted to predict, use jump time to predict sprint, I would have to use number two. So number two is the correct equation. So this is correct this is the correct equation, number two, for this problem. Yeah, so for this problem, if I'm starting with jump distance and I want to predict time, I would have to use this equation. I could not use the original equation to do that. Okay. One more piece of information, I think, or maybe trying to think. I want to do next page. There's not a ton left on the next page, but just a brief intro to what least squares regression means. So least squares regression. So imagine here drawing the residual for every single point. So if you drew the residuals in, that would be the distance, the vertical distance between the actual y value and the y value predicted on the line. So if we drew in these would be all of the little residuals. Okay, so I could draw lots and lots of little residual values. Okay, some of these are practically right on the line, but this would maybe have just a teeny positive residual and a teeny negative residual. Now, if we added up all of these residuals, a residual value is going to be positive. So these are positive residuals above the line. And these would be negative residuals below the line. Because if I take the actual minus the predicted, the actual is actually less than the predicted there, so I would end up with negative numbers. So these are negative residuals below the line. Guess what happens if I add them all up? What do you get? 0. Yeah, if I take all the positive residuals and I add them up to all the negative residuals, I end up with 0 residual. This is the same thing that happens if we add up all the deviations from the mean. You add up with 0. Yeah.
So is this how they find the line? They make it so all the residuals add to 0?
No, actually, they add up. They square all those numbers and they minimize the sum of the squares. Is what they do. So, because you potentially could have more than one line where the residuals would add up to 0. No, maybe not. Yeah. I don't know. That's a good question. I'm not sure. But the residuals add up to 0. So since they add up to 0, we do the same thing we did when we did the standard deviation formula, or when we did the chi-squared test statistic. We square everything. So we get one number that represents all of the amount of error. So we square all those numbers. That's why there's these little squares there. So if we add up the area of all these squares, the line that minimizes the sum of the squares is the best fit line. So that is why it is called the least squares regression line. So there's actually a number here, the sum of the squares. This is actually a measurement of the area of all these little residuals squared. And whatever line yields that minimum value is the least squares regression line. And I just wrote that out. If the actual mathematical process is, since these are all squared values, you end up getting a rather complicated looking quadratic formula, and you're finding the vertex of that parabola, which would be the minimum value, which involves using calculus and derivatives and so forth. So there's all of this gets calculus in there eventually. Calculus ends up being behind all of the things you do in statistics, almost everything. Cool. Yeah. Okay. So this is not something that I don't believe that you will be asked to ever explain why it's called least squares regression, but I just wanted you to know that's why it's called. And so very often you will see in statistics, in books and stuff, this abbreviation for least squares regression line. So if you see LSRL, that's what they're talking about, is the regression line formed by this method. There actually are other ways to find best fit lines. There's something called a median line and some other there's other techniques, but this is the most commonly used one. Pardon me? No, they don't all get the same results. I think that maybe the advantage of the other method is that you can do it without calculus. So it's more of a more, I don't know. It's a mathematically based method that is more accessible to people who don't have prior to calculus or without technology. Okay, so the last little piece I want to talk about today is residual plots. So if you have your least squares regression line, if you were to if you were to just plot the residuals. So if we were just to take all of the residuals and plot them against their x values. So let's say, for example, we just found this one residual here. This was a residual of 22.61. It happened when x was 5.78. So what we see down here is just the residuals plotted. So in other words, here's the point 5.78 and here's the point 22.61. Okay, so this is the residual plot. This little line maybe this has a negative residual, maybe of negative 30 or negative 25 or something. So right over here, this would be a residual of negative 25. So this residual plot just plots the residuals for each of the points. And notice, if you just take this line and make it level and look at it, where the points are located is exactly the same as they are here. They're just spread out a little bit more. But you can see here these 2 points. Here's this point above the line. Here's this point below the line. Here are these 2 points above the line, and then here's those 2 below, and so forth. And you can see this one's really close to the line. So these are just these same points plotting their residuals. Now, what do we want to look for when we look for a residual plot? You know how we have conditions for all the other models we use? Well, linear models have conditions too. And one of the conditions for using a linear model is that the data is actually linear. Duh, that kind of makes sense. Like, you only use a normal model when the data looks like a normal model. It doesn't make sense for other types of data. So we want to look at 2 things when we say, is a linear model appropriate? Number 1, you look at the scatter plot. Is the scatter plot fairly straight? And you might say, why didn't I say, is the scatter plot fairly linear? The reason I didn't say it that way is I graded a problem one year in AP Stats where you were supposed to answer this question, basically, is a linear model appropriate for the data? And if you said a linear model is appropriate because the data is linear, they counted that as a circular argument where you were using the word that you were trying to define. You had to say something like the points go in a straight line or the points are straight. So that's why I'm saying maybe avoid using the word linear if you're trying to define what's linear, you know? So is the scatter plot fairly straight? Number 1. Number 2, you're looking at the residual plot. Is the residual plot randomly scattered with no obvious bend or curve? No, you don't say skew. You're looking for, because we're looking for something where the data curves, all right? We want to know, is it linear or is it curved? So I don't see any particular pattern of a curve in here. It looks pretty randomly scattered to me. So I would say both of those are correct. Both of those are correct. So a linear model would be appropriate for these data. Okay. So let's look at 2 other examples. These were from some data that I gathered in a previous class several years ago. I thought this was a fun thing to try. Had the students measure the length of their longest piece of hair and record their shoe size. Now this was a little more variable, but what would you expect? You would expect the people with smaller feet were girls and they might have had longer hair, right? So as the shoe size increased, the length of the hair decreased, but you do have some girls with short hair and some guys with longer hair. So there was a lot more variability in this data. It wasn't as strong of a linear association as whatever that previous thing was, the sprint and jump thing. But it was still, if we look at the scatter plot and we look at the scatter plot and we look at the residual plot, there is no obvious bend in the data to indicate that it's not linear, okay? It's not a strong linear relationship, but it is still a linear relationship for the most part. And we got an outlier here. So this was a person with fairly small feet and fairly and actually really long hair, looks like extra long hair. And then we had someone here. Oh, it looks like I didn't show the bottom part of the scatter plot. Looks like I cut it off a little bit. There's someone here with really big feet and maybe a little bit longer hair than expected. But we still have yes. Okay, so 1, the scatter plot. Looks reasonably straight. Looks reasonably straight. Now, when I say that there's no obvious bend, okay, yeah, it can be scattered. Scatter is okay. Okay, scatter is okay. Just not bent, you know. But I double check this. I don't see any obvious bend. Okay, so no obvious bend in residual plot. Okay, so that looks okay. And usually you can tell from the scatter plot alone, but not always. And that's why you always want to check the residual plot too.
What's the residual plot compared to the
Pardon me?
What's the residual plot compared to the top graph?
The residual plot just shows all the differences from 0 of each of the residuals. So like this is above, the difference in the 2y values is above 0 here. The differences in the 2y values down here would be below 0, like actual minus predicted. And so here are all the places where the actual values are higher than the predicted values, and here are all the ones where the actual values are lower than the predicted values. But this just tells how much lower or higher they are than predicted.
So it's not actually 0, it's just
Well,
0 compared
what
to
would 0 residual mean? What does 0 residual mean?
It's on straight line.
It's on the line.
Exactly a point on the line where the actual and the predicted are almost exactly alike. Yeah, so these would be ones with 0 residual. So these points are all the same as these points, only instead of putting the x and y value coordinates, the x value is still the same x value, but the y value is the residual. It's how much different the y value is from the predicted. Okay, this was the one I wanted to, the last one is the one that I wanted to show you, is that sometimes when you look at the scatter plot, it looks reasonably linear, but when you look at the residual plot, you notice the exact, since it spreads the data out, you see the curve. And this turned out to, this was a problem where I had a bunch of different size lids, and I had people put Cheerios in to fill in the lid, the area of the lids. And so basically the x value was the radius of the lid, and the y value was the number of Cheerios needed to fill up the lid. Well, that is not a linear function, because area is a quadratic quantity because it's something squared. Area is like pi r squared for a circle. So we would expect that to have more of a parabolic shape, a curved shape. But when you look at the scatter plot, I had a lot of small lids and only a couple of big lids. It really made it look more linear than it actually was. So the scatter plot looked linear, but you can see the bend in the data. So this is one for where a linear model is clearly not appropriate. We have this big bend. So the bend in the residual plot shows that this data is curved and not linear. So I would say no, and not linear. So this is just why we check the residual plots and what the residual plots are telling you. You could also look and see on a residual plot like which values were lower than predicted, which values were higher than predicted. Yeah.